This is the fourth and final part of the 11th lesson in heat transfer. We have been looking at the finite volume technique for analyzing steady-state, multi-dimensional conduction heat transfer problems. In this final part of the lesson, we will derive the governing finite volume equation for a boundary node. By the end of this lesson, you should feel comfortable deriving governing equations for any boundary node in a numerical mesh. On with the lesson. Recall that a finite volume analysis always consists of three main steps: discretizing the domain by creating a numerical mesh, identifying the governing finite volume equations for each volume in the mesh, deriving one if required, and finally solving those coupled set of algebraic equations. We have been focusing on step 1 and step 2 in this lesson, and we will again look at step 2, looking at the governing equation for a boundary node. Here is an example of a node on the boundary of a numerical mesh. At this part of the mesh, there is a corner, and a node has been placed on the corner. On the inside of the mesh, there is conduction heat transfer. This corner of the mesh is exposed to a fluid that is flowing. The convection heat transfer on the face is characterized by a convection heat transfer coefficient H and a fluid temperature T infinity. We desire to determine what the equation is that governs the heat transfer in this volume that is coincident with the boundary. I again replace the nodal indices M and N with alphanumeric N, S, W, E, and P. So we do not have to continue to write the indices M and N. We can replace those again later. So we have the node point of interest P, the node to the west of that node, the node to the east, the node to the north, and the node to the south. We assume that all the heat transfer is in across each face. This is always the assumption when deriving governing equations for the finite volume technique. Here we have conduction heat transfer across the north face, because the north face resides inside of the physical problem. Across the west face, we also have conduction heat transfer. Across the south and east faces, the situation is a bit different. Here we have conduction heat transfer across the part of the east face that resides within the solid, and we have convection heat transfer across the part of the face that is coincident with the boundary on which there is convection heat transfer. Similar condition exists for the south faces. Part of the south face resides in the solid, and here we have conduction heat transfer. Another part of the south face is coincident with the boundary on which there is convection heat transfer, and here we have convection heat transfer. Across each face, we assume that the heat transfer is in. We apply the heat transfer energy balance equation. We have a steady state heat transfer, and all of the heat transfer is in. Here I have denoted each of the four conduction heat transfers across the west, east, south, and north faces. And we have the convection heat transfers across the east and south faces on the corner. Finally, if there is thermal energy generation, it is included here, assuming that the thermal energy generation is a constant in the volume. We now apply the rate equations for heat transfer. We start with the conduction heat transfer. We apply Fourier's law for the rate of heat transfer by conduction and assume linear variations in temperature from node to node. Doing so allows us to substitute in for the temperature gradient at each of the faces across which there is conduction heat transfer: the west face, north face, half of the east face, and half of the south face. We also substitute in the areas associated with the heat transfer, since Fourier's law provides an equation for the heat flux, and we are interested in the overall rate of heat transfer. We have thus multiplied the flux by the appropriate area. I have denoted that the area of the east and the south face is slightly different than what we saw in the previous video, because these areas represent half of the face only. For details on this substitution for the temperature gradient, please see Lesson 11 Part C. We now apply Newton's law of cooling for the rate of heat transfer by convection, and we assume that the corner surface temperatures are all at Tp. One may think, why is this allowed? We just assumed that the temperature varied linearly from the east node to the P node, but that was in the formulation of the conduction heat transfer. The finite volume analysis, we are allowed to choose different interpolation profiles for different processes occurring within the volume. So for convection heat transfer, we will assume that the temperature is uniform across these faces, all at the temperature Tp. This is valid in our approximation of the solution. Applying Newton's law of cooling, we have the convection heat transfer coefficient times T infinity minus Tp, because we are assuming that the heat transfer is from the fluid into the volume. We have the source temperature and the sink temperature. And I've denoted, again, the appropriate areas, which are half of the faces. We now substitute in for the areas of each heat transfer and also the relationship for the volume delta V, relating these areas and volumes to the nodal spacings delta x and delta y. On the west face, the area of the face is the nodal spacing delta y times 1. We are dealing with a two-dimensional problem, so we are allowed to set the third dimension, the depth of this mesh into and out of the page, equal to unity, 1 meter. We are conducting our analysis on a per unit meter basis. Similarly, the north face is equal to the spacing delta x times 1. The east faces are broken into two pieces. Each represents delta halves times 1, since the face is broken down the middle in this mesh. Similarly, for the south face, the area of each part is equal to delta x halves times 1. Finally, we note that the volume of this on the corner is 3/4 the volume of an interior node. So we can simply write 3/4 times delta x times delta y times 1. We now substitute in these expressions for the areas and the volume. The resulting equation is as follows. We will now simplify this equation. If the nodal spacing in the x and the y direction are set to be equivalent, then the delta x and delta y cancel as follows in the conduction terms. And we can replace the delta x and the delta y with just delta x, since delta x and delta y are equal to one another. In the generation term, delta x times delta y becomes delta x squared. If we now continue to simplify this equation by dividing through by the thermal conductivity K, then we are left over with the following. We now group all terms that are similar. We have multiple T sub P's. Some of the T sub P's are half. Combining together, we have a minus Tp, another minus Tp, that's 2, and then a half of a minus Tp and a half of a minus Tp, for a total of minus 3 Tp. We also have combined the half of the h delta x over 2 into 1, and factored the h delta x over k through to T infinity and Tp. Notice that we have a minus 3 Tp and a minus h delta x over k Tp. these terms can be combined to give the following form. If we replace the P, W, E, N, and S with the appropriate node indices, then we have the following equation for the temperature of the node at this corner volume. This is equation 4.41 from your textbook, except that in equation 4.41 it is assumed that there is no thermal energy generation. One simply sets the Q triple prime equal to 0. This equation assumes that the nodal spacing in the x and the y is equal, and also that the thermal conductivity is equal to a constant. I think that it is valuable to compare this governing equation from the governing equation for an interior node derived in the third part of this lesson. Here is that equation repeated for convenience. Note the differences. Both equations feature the nodal temperatures of the neighbors. In the boundary node, however, those neighbors that are also on the boundary, where the face is broken into two pieces, have a coefficient of 1/2 rather than unity. One might think that that's because half of the face experiences conduction heat transfer, which is where these temperatures come from. In the interior node, 4 times the nodal temperature T sub P, or T sub Mn, is subtracted from the equation. Here on the boundary node, we subtract 3, plus an additional subtraction associated with the convection heat transfer. Finally, we note that because of the convection heat transfer, there is an additional constant term associated with the T infinity. This is not present in the equation for the interior node because there is no convection heat transfer here. This could also apply to a different corner. One would simply swap out the coefficients associated with the appropriate node on which the corner was. For example, if this were a northwest corner, we would swap out the 1/2 and put it on the west and the north faces, leaving 1s on the coefficients for the south and the east. As a final note in this lesson, there is a table in your textbook which provides a reference for finite volume equations, including the equation for an interior node and equations for common boundary conditions. This is table 4.2. It will be a useful reference. The equations in this table assume that the thermal conductivity is equal to a constant and that the nodal spacing in the mesh is equal, delta x equals delta y. The equations exclude energy generation. One can account for energy generation by simply adding Q triple prime times delta V, where delta V is one of the following conditions, depending on the location of the boundary node. For an interior node, delta V is delta x squared times 1. For an interior corner, 3/4 delta x squared times 1. For a boundary node on the face, 1/2. And for a corner, 1/4. Finally, directions can be generalized. Replace W and E and so on if the node is on a different face of the physical problem than that depicted in the table. This is the end of the 11th lesson.